So welcome back. We're on page 4 of your shapes notes, and we're going to look at molecules with double bonds like CO2 and SO3. So if you look at the first example, CO2, it has 2 sigma bonding pairs. It also has 2 pi pairs, but because the sigma and the pi pairs lie in the same plane, we say it's only got 2 areas of electron density. It's got no lone pairs, so the lone pairs plus the sigma bonding pairs, or the lone pairs plus the areas of electron density, are 2, so it's linear. In terms of electron pair arrangement, because there are no lone pairs, the electron pair arrangement and the shape are the same, so it's linear. And the carbon dioxide, therefore, is a planar molecule with a bond angle of 180. Same for the SO3. I have 3 sigma bonding pairs, or 3 areas of electron density, no lone pairs, so therefore the position is trigonal planar, and because of the no lone pairs, it is therefore the same as the shape, and we have S double bond to my 3 oxygens, and my bond angle again is 120. So in this case, the double bonds have no effect on this shape. So here is a classic question from the exam. So you're comparing ammonia with water with methane. Now the reason we want to compare these 3 is they all have the same number of bonding pairs plus lone pairs. So their electron pair arrangement is all tetrahedral. So in ammonia's case, I have 1 lone pair and 3 bonding pairs. Water, 2 lone pairs, 2 bonding pairs. And in methane, I just have my 4 bonding pairs. So the first thing to say about this is that they all have a tetrahedral electron pair arrangement, as they all have 4 areas of electron density. Then we need to say something about the fact that therefore those will separate out to maximize separation or minimize repulsion. The fact that the lone pair has a greater repelling effect than the bonding pair, and that lone pair has a greater repelling effect than lone pair bonding pair, hence the reduction in the bond angle for water. So they all have these 4 areas of electron density, but because lone pair repulsion is greater than lone pair bonding pair repulsion, which is greater than bonding pair repulsion, and because they all separate out to maximize separation or minimize repulsion, you get this difference in the bond angles. But this rule doesn't only apply to molecules, it also applies to ions in exactly the same way. So if we consider the ammonium ion, so you have nitrogen, which is now covalently bonded to 4 other hydrogens. Now we've come across this molecule before, and you might remember that because it's the ammonium ion, the ammonia has gained a hydrogen ion, so it's used its lone pair there to form a dative covalent bond. But once that dative covalent bond is formed, it's exactly the same as any other covalent bond. So I now have 4 sigma bonding pairs, 4 areas of electron density, no lone pairs, so it's a 4. The electron pair arrangement is still tetrahedral, but because we've gained a bonding pair of electrons, we've lost a lone pair, the electron pair arrangement is now the same as the shape. So you have your nitrogen. I'm going to draw that one as my dative covalent. That's why there's an arrow there. And then H and H and H. And the bond angle has increased to 109.5 because that lone pair has become a bonded pair. I can do the same thing for the hydroxyl ion, H3O positive, where again the oxygen has used one of its lone pairs to form a dative covalent bond with that hydrogen ion. I should put a positive on both of these. So again, that lone pair is there, and then 2 just normal hydrogen oxygen bonds, single bonds there, and with my 1 lone pair of electrons left over. So here I have 3 areas of electron density, 3 sigma bonding pairs, 1 lone pair, again, total of 4, so it's based on tetrahedral. But again, in this case, because you've got a lone pair there, the shape and the electron pair arrangement are not the same, but oxygen, this molecule, now looks, do the hydrogen there, hydrogen, and a dot hydrogen, because now you've got 3 bonding pairs and 1 lone pair. This would be trigonal pyramidal. And because one of those lone pairs has become a bonding pair, the bond angle is increased from 104.5 to 107. In other words, it looks a lot like ammonia. So the last example is SO3 2-. Sulfur is one of those ones, remember, where you can expand your octet, but oxygen you can't. So I have 3 oxygens. You've got a 2 negative charge, so 2 of those oxygens have gained an electron from somewhere else, which means they're going to form a single bond with my sulfur. And then the last oxygen is forming my normal double bond. Put the electrons back in. Sorry, I need some more there. But notice I've only used 1, 2, 3, 4 of my sulfur's outer shell electrons, so it now has a lone pair as well. So again, counting sigma bonds, I have 3 sigma bonds, 1 lone pair, so it's a 4. So again, it's tetrahedral. But because it's a 3-1 split between sigma bonding pairs and lone pairs, it's the same shape as the ammonia or the H3O positive ion. So you've got sulfur. You've got a single bond to an oxygen. I'm going to put the negative on there. Single bond to another oxygen and a double bond. Should do that as a dotted line to the last oxygen. And you have the lone pair here. So the bond angle is still 107 and it's still trigonal pyramidal. Now, obviously these numbers will change slightly depending on the atoms that are actually involved, but 107 is a good enough approximation for pretty much all trigonal pyramidal molecules. So in terms of bond lengths, so this is the distance between the 2 nuclei of 2 atoms linked by 1 or more covalent bonds. Notice the larger the atom, the longer the bond is going to be. So a sulfur-sulfur bond is going to be longer than an oxygen-oxygen bond, always. So if we compare things where we've got the same atoms but we're just changing the number of bonds, you should see that a single bond is longer than a double bond, which is longer than a triple bond. And this also relates to the strength. So the shorter the bond, as we go down, the stronger the bond becomes. And in this case, I have a sigma and 2 pi for my triple bond. So we're back to our old favourites, size and charge, and in this case it's to do with size, so the shorter bonds means the stronger bond. So we can not only apply this to inorganic molecules, but also to organic molecules in exactly the same way. So if we look at the alkane, we have carbon with 4 sigma bonds around it. So all the bond angles in this are 109.5, and the shape around each carbon atom is tetrahedral. They're not the easiest things to draw, but this is why when, for example, we do a skeletal formula, you draw this as a zigzag. The reason you draw them as zigzag is because then the bond angle is 109.5, and that's why the skeletal formula looks like this. Alkenes, on the other hand, because you've got 3 areas of electron density, 3 sigma bonds around each carbon, these values are back to 120. So that's a 120 bond angle. Now, the length of the double bond, remember, double bonds are going to be shorter and stronger than single bonds. So this is a shorter bond. And the 3D diagram shows exactly the same as the normal diagram because it's a planar molecule. As we have more complex molecules, we can have a variety of bond angles and shapes. So for example, in an alcohol, you still have your tetrahedral arrangement around the carbon, so you still have 109.5, but because you have an OH group, oxygen still has its lone pairs, this bond angle is your typical 104.5. So you have two different bond angles. Halogenalkanes like bromomethane, doesn't really matter that I've replaced the hydrogen with a bromine. All that's going to happen is this bond length is going to change, but the angle is going to stay the same. So because you've got 4 bonding pairs, no lone pairs, it's still 109.5 between each of these bonding pairs of electrons. Last but not least, on this page, we're going to look at various bond angles. So in this one, methanoic acid, I'm interested in this bond angle here, and that, because you've got these 3 areas, is 120. Here, again, you've got that oxygen with the lone pair, so this is going to be 104.5. Here, this is an aldehyde, propanal, but again, notice 3 areas electron density, and again, I've got a 120 bond angle. Here, you've got propanone, and we've got 2 different bond angles. So I've got a bond angle here of 120, and a bond angle here of 109.5. This is tetrahedral.